Have you ever really thought about what happens when you throw something? I mean, really thought about it. That perfect arc, whether it's a baseball or just a wadded up piece of paper headed for the trash can, well, it follows this universal set of rules. Today, we're going to pull back the curtain and dissect that arc to understand the incredible physics that makes it all work.
So, what is the secret to a perfect throw? Is it just about having a strong arm? Well, that helps, for sure. But the real secret, the blueprint for every single throw, is written in the language of physics. And by the time we're done here, you're going to know how to read it. Let's dive in.
All right, here's the game plan. We'll start by looking at the beautiful shape of that flight path, what we're calling the perfect arc. Then, we'll figure out how to actually measure its journey. After that, we'll open up our physics toolkit, put it to the test with a real-world problem, and finally, we'll uncover some seriously cool secrets that are hidden inside the math.
Okay, first up, the perfect arc. You see, any object flying through the air, and I mean anything, from a cannonball to a basketball, follows this really elegant, predictable curve. It's called a parabola. And the reason why is fascinating. It's because the object is secretly on two different journeys at the exact same time.
Think about it like this. Horizontally, the object is just cruising. It's moving forward at a nice, steady speed, as if nothing else is happening. But vertically, oh, that's a different story. It's in a constant battle with gravity. It fights its way up, slowing down. It hangs for just a split second at the very top, and then gravity wins, pulling it faster and faster back down. It's this combo, the steady forward cruise and the up and down drama, that creates that perfect parabolic arc every single time. So we get the shape, but how do we actually, describe it with numbers? To really get a handle on a projectile's flight, we just need to measure three key things: how long it's in the air, how high it actually gets, and how far it goes. First up is what we call the time of flight. This is super simple. It's the total hang time, from the second it's launched to the second it lands. And remember that vertical battle with gravity? Well, this number is decided entirely by that. It's just how long it takes gravity to bring the object back down. Next, we've got the maximum height. This is the absolute peak of the journey. And something really cool happens here. For a tiny, tiny instant, the object's upward motion completely stops. Its vertical velocity is 0. It's not going up anymore, and it hasn't started coming down yet. It's just hanging there at the top, even while it's still moving forward. It's a pretty critical moment. And last but not least, the horizontal range. Honestly, this is the one we usually care about the most, right? How far did it go? It's just the total ground covered from the launch point all the way to the landing spot. Okay, so we know what we want to measure, but how can we figure all this out before we even throw the thing? Well, this is where we break out the physics toolkit. Now, don't let the equations scare you. These aren't just formulas. They're like these three amazing gadgets that let us predict the entire flight path. And here it is, the whole toolkit. It looks kind of complex, but it all boils down to just 3 bits of information. U is your starting speed, how fast you throw it. Theta is the angle you launch it at. And G is just the constant pull of gravity. That's it. You give me those 3 things, and these formulas can tell you the future. All right, enough with the theory. Let's actually put this toolkit to work. Let's imagine we've got a projectile. It's fired at a speed of 50 meters per second, and it's launched at a pretty steep 60-degree angle. Our mission, should we choose to accept it, is to use our new tools to figure out its time, its height, and its range. Let's start with the time of flight. We grab our formula and we just plug in the numbers. 50 for the speed u, 60 degrees for angle theta, and we'll use a nice round 10 for gravity g, just to keep the math easy. So that's 2 times 50 times the sine of 60 degrees, which is about 0.866, and then we divide that whole thing by 10. And what do we get? Boom, the projectile is going to be in the air for 8.66 seconds. That's our first answer, locked in. Okay, what about the height? How high does this thing go? Let's grab the next tool from our kit. We square the speed, so 50 times 50 is 2,500. We multiply that by the sine of 60 degrees squared. Then we take all of that and divide it by 2 times g, which is 20. And the answer is 93.75 meters. To put that in perspective, that's pretty much the height of the Statue of Liberty. So yeah, this thing is going way up there. All right, last one. How far does it go? We pull out our third and final formula. Now pay attention here. This one uses the sine of 2 times the angle. So we need the sine of 120 degrees. So we take our speed squared, 2,500, multiply it by that result, and divide the whole thing by 10.
And there we have it. The total distance it travels is 216.5 meters. That's more than the length of 2 football fields. See? We've just mapped out the entire flight of this projectile without even having to watch it. That's the power of physics.
So we've seen that the toolkit works. But now for the really fun part. Let's uncover some of the secrets these equations can tell us. Because they're not just for crunching numbers. They reveal some really deep, sometimes kind of weird, truths about the way things fly.
Check this out. This is one of the absolute coolest secrets of projectile motion. It's called complementary angles. Let's say you throw a ball at a low 30-degree angle. It takes a low, fast path. Now, throw it with the exact same speed, but at a high 60-degree angle. You get this big, looping arc. They look totally different, right? But believe it or not, they will land in the exact same spot. The range is identical. And this works for any 2 angles that add up to 90 degrees. Wild, isn't it? So that leads to the ultimate question, doesn't it? If different angles give different results, what's the one single angle that gives you the absolute maximum possible distance? The answer is a perfect 45 degrees. It's that sweet spot, the perfect balance between going up for hang time and going forward for distance. No matter how hard you throw something, 45 degrees is always going to get you the farthest downfield. Okay, let's leave you with a little brain teaser to chew on. We know that at the very peak of its flight, a projectile's vertical speed is 0. All that's left is its constant horizontal speed. So here's the puzzle. If the speed at that peak is exactly half of the speed it was launched with, what was the original launch angle? The answer is right there, hiding in the physics we just talked about. Think about it.